Let's investigate this research question. Is people's interest in the environment associated with their level of education? So this is data from the 2018 General Social Survey on the number of people in a sample who either had or did not have a college degree, and whether they said they were very, moderately, or not interested in environmental issues. Here, the null hypothesis is that there is no association or no relationship between a person's level of interest in the environment and whether they have a college degree. Another way we could write this would be to say that level of interest in the environment is independent of whether a person has a college degree. And in symbols, we could write pi sub very equals pi sub moderately equals pi sub not, where pi sub very is the probability of having a college degree among the group of all people who are very interested in the environment. The alternative hypothesis is that there is an association between a person's level of interest in the environment and whether they have a college degree. Or we could say that the alternative hypothesis is that at least one of the three probabilities of a college degree is different from the others. So the alternative hypothesis is not that all three of the groups have a different probability of a college degree, just that at least one of them is different. Here, we're testing for an association between two categorical variables. So on first glance, we might think that we should consider using a two-proportion z-test. But one of the categorical variables, interest in the environment, is non-binary. So a two-proportion z-test won't work. Another way to think of this is that we're comparing the proportion of college degrees between three different groups, not two different groups. The type of theory-based test to consider in these circumstances is a chi-squared test of independence. This is a theory-based test of association between two categorical variables, where the categorical variables can have any number of categories. They might be binary or non-binary or one of each. We could also think of this as a theory-based test comparing proportions among any number of groups. The validity conditions for the chi-squared test of independence are that all the expected counts should be at least 1, and not more than 20% of the expected counts should be less than 5. By expected counts, we mean if the null hypothesis were true and all three groups were equally likely to have a college degree, how many people would we expect to have in each of the 6 cells of the table summarizing our data? The video on simulation-based tests comparing multiple proportions discusses how to compute these expected counts by hand. We'll see how to compute them using a calculator function later in this video. If the validity conditions for a chi-squared test of independence are satisfied, then the null distribution of this test statistic will have approximately a chi-squared distribution. So the test statistic is the same as in the simulation-based approach to testing multiple proportions. It's the sum over all the cells in the table of the observed count for that cell minus the expected count for that cell, quantity squared, divided by the expected count for that cell. A chi-squared distribution is sort of like a normal distribution in that it's a shape that we might see for a histogram of quantitative continuous data. But unlike a normal distribution, a chi-squared distribution models right-skewed data that can't be negative, which makes it a good model for the test statistic we saw on the previous slide, which can't be less than 0. Where we had a normal distribution having parameters mean and standard deviation to control the shape, the chi-squared distribution has the parameter degrees of freedom, where the larger the degrees of freedom, the less right-skewed the distribution becomes, and the closer to a normal distribution. In a chi-squared test of independence, the degrees of freedom are equal to r-1 times c-1, where r is the number of categories in the row variable of our table, and c is the number of categories in the column variable of our table. In our environmental example, we have 2 categories for the row variable, has a college degree, and 3 categories for the column variable, interested in environmental issues. So the degrees of freedom are 3 minus 1 times 2 minus 1, so 2 times 1 equals 2. A chi-squared distribution with 2 degrees of freedom looks like this. So if the validity conditions for a chi-squared test of independence are satisfied, then we expect the null distribution of our test statistic to have this shape. And it turns out that the validity conditions will be satisfied, and if you put this data into the multiple proportions applet, you can see that the null distribution of our test statistic does follow that right-skewed shape. Here's how to do a chi-squared test of independence on a TI-83 or TI-84 calculator. The way this is going to work is that when we suspect that a chi-squared test of independence is going to be appropriate, we go ahead and do that test, and as part of the calculations, our calculator will compute the expected counts for us. So once we've done the test, then we can check the expected counts to check if the validity conditions for the test were satisfied. So to do this, press the second key and then the matrix button, which is the same key as x to the negative 1. Choose Edit, and then press Enter to edit matrix A. Put in the dimensions that you want, the number of rows and the number of columns, and then enter the observed counts from the table summarizing the data. Then press the Stat button and choose Tests, and then chi-squared test. The value after observed should be the matrix where you stored the observed counts, and the value after expected should be the matrix where you want the calculator to put the expected counts. Go ahead and give this a try on your calculator for the environmental issues dataset. For this test, your calculator gives you 3 pieces of output. Chi-squared is the test statistic, the observed minus expected squared divided by expected for each cell, added up over all the cells in the table. DF is the degrees of freedom, so that should match the rows minus 1 times columns minus 1. And P is the p-value. This is the area under the chi-squared curve to the right of the test statistic. Before we actually interpret our p-value, we need to know whether using the chi-squared test of independence was appropriate. That is, were the validity conditions satisfied to make the chi-squared distribution be a good approximation for the null distribution. The validity conditions for a chi-squared test of independence deal with the expected counts, so we need to check those. We can do that by pressing second and then matrix again, and choosing Edit and then matrix B, the matrix where we told the chi-squared test to store the expected counts. Here's what the expected counts look like for this dataset. Recall that the validity conditions for a chi-squared test of independence were that all expected counts should be greater than or equal to 1, and not more than 20% of the expected counts should be less than 5. Here, all of the expected counts are greater than or equal to 1, so we have a check for that validity condition. The table of summarizing the data has 6 cells in it, so 20% of that would be 1.2. So we need not more than 1.2, or not more than 1 of the cells to have a number less than 5 for the expected counts. In this case, all of the cells have expected counts at least 5, so we're good to go on that validity condition too. This means that the validity conditions for a chi-squared test of independence are satisfied, so we can trust the p-value. It's going to be close to what we would get using the multiple proportions applet to compute a simulation-based p-value. In this case, our p-value was very small, so our conclusion could be that at a 0.05 level of significance, there is enough evidence to claim that a person's level of interest in the environment is associated with whether they have a college degree. Or we could say there is enough evidence to claim that at least one of the 3 probabilities of a college degree is different from the others. From this test, we don't know which of the probabilities of a college degree is different from the others, or if they're all 3 different from each other. In order to determine this, we would need to conduct 3 separate 2-proportion z-tests. But the advantage of doing a chi-squared test of independence first is that it can save us a lot of work in the event that we get a large p-value, and it turns out that, nope, it is plausible that all 3 of those probabilities could be equal to each other. If the validity conditions for a chi-squared test of independence aren't satisfied, we have 3 options. 2 of these are the same as the options that we had for other types of hypothesis tests we've talked about this semester. We could find a simulation-based p-value instead of a theory-based one. In this case, that would mean using the multiple proportions applet. Or we could gather more data. By increasing the sample size, we can increase the expected counts in each cell. The third option is unique to the chi-squared test of independence and other tests that can be used to compare more than 2 groups. And that is to combine categories. For example, suppose we had this table of expected counts across 2 groups and 3 answer options, A, B, and C. This table has 4 out of 6 cells with expected counts less than 5. So we're not meeting the validity condition that not more than 20% of the cells can have expected counts less than 5. But if we combine answer options B and C into an overarching group B or C, now the expected counts in each of those cells are 6. So we are meeting the validity conditions for a chi-squared test of independence.